So welcome back, everybody who's online and some of the people that are joining us here. We will start the first talk after lunch with Professor Sliman Bensmaia. He's been working a lot on the sense of touch, and that's a very relevant research for the work we do here and many others on neuroprosthetics. So we're happy to have you, Professor Bensmaia, please.
Is my slideshow coming up, or do I need to press this thing?
It's going to come.
Okay. Oh, there it is. Well, thanks for having me, Max. It's good to be back to Gothenburg. So before I get started on the meat of the talk, I just want to frame it by just telling you a little bit about what we spend most of our time doing in my lab, which falls under the rubric neural coding, and I'm going to be talking about touch, so I'll use touch as an example. So what we do is, we're interested in understanding how sensory information is encoded in the nervous system. So here you see this squiggly line here represents, when we interact with an object, it starts with a spatiotemporal pattern of deformation of the skin. That's what this squiggly line is. And there are mechanoreceptors that people were talking about earlier that convert these skin deformations into patterns of neural activity first in the nerve, and that neural activity then propagates down the neuraxis, cuneate nucleus, thalamus, several stages of processing in cortex, ultimately giving rise to a percept of this object. And when we hold an object in the hand, we can perceive its shape, we can sense its shape, its texture, its motion across the skin. And all that information is encoded in these patterns of neural activity. And what my lab spends a lot of time trying to figure out is how is information about texture, or how is information about shape of objects or motion of objects encoded in these neural patterns of activity at each stage of processing. And so, actually, before I move on, I'll just say that I'm not going to spend, this is not what I'm going to talk about today, but everything I'm going to talk about today is informed by this sort of basic scientific understanding of the sense of touch, which we're then going to try to leverage when creating or trying to restore it. But before I go into that, let's just spend a few minutes talking about why are we going to spend time trying to restore the sense of touch. So this is a movie I made of me doing a bunch of stuff with my hands. Most of it is mundane stuff like picking things up or writing with a utensil or typing on a keyboard. And these are things that you could not do without the sense of touch, because anytime you're interacting with an object, you get this barrage of sensory signals coming back from your hand that's telling you about your interactions with the object and the object itself. And without these sensory signals, we would struggle to use our hands. So this is a movie made that probably a lot of you have seen by Roland Johansson at Umeå University, of a lady lighting a match. Same lady moments later is trying to do the same thing, except her fingertips have been numbed with a digital anesthetic, and now she struggles mightily to do this task. And she drops a match, she tries to pick it up, realizes she's not going to be able to do it. And finally, after a long struggle, she lights this match, and she's going to do this over and over again, and she's going to continue to struggle because the visual system is just not well equipped to provide her with the information she needs to perform this task. Now, this individual here suffers from a peripheral neuropathy that's destroyed his entire somatosensory system. He has no sense of touch or proprioception anywhere in his body, and he's doing something even easier than lighting a match. He's just trying to grab this coffee cup and bring it to his mouth, and as you can see, he struggles to do this, as he does everything else. And if I showed you this and I asked you, what do you think is wrong with this guy, you would probably think he has some kind of motor impairment. And it really it highlights the yin and the yang between the motor and the somatosensory system, where really one does not work without the other. So now in the context of prosthetics, which is what we're here to talk about, the same thing is true. So this is a movie made by my colleagues at the University of Pittsburgh of Jan here, who has been equipped with an array in the motor parts of an array, primary motor cortex. And without going into details, because that's not the focus of my talk, she can control this robot volitionally. Basically, in short, my colleagues have created algorithms that can read out her motor intent from these signals in the brain, and then they make this robot do it. And you can see her doing this task. She's moving these objects around, and if you're seeing this for the first time, which probably none of you are, you're thinking, well, what a great scientific and technological achievement, but then you realize how much better you would be at this if you were doing it. You would be moving these objects with much more rapidity, and dexterity, but her performance is comparable to the performance of this last guy I showed you, who had an intact motor system, an intact limb, but no sensory system, or no somatosensory system. So the idea is, if you're going to achieve a dexterous prosthesis, you're not only going to have a sweet robot and some great control signals, but you're also going to have to restore the sensory signals. So how do we do this? This is sort of a movie to sort of illustrate the general approach. The idea is when you're interacting with an object, the skin deforms. It produces a pattern of activity in nerve fibers that innervate the skin. And this activity travels up the arm and ultimately culminates in a pattern of activity in the somatosensory cortex. So this is the part of the brain that receives input from the whole body, right? And that pattern of activity in the somatosensory cortex depends on what you touch and how you touch it. Now, these prostheses, many of these prosthetic hands have sensors on them. And so what we work on is to develop algorithms that take the output of these sensors and converts them into patterns of electrical stimulation delivered to the somatosensory cortex to try to reproduce these patterns of activity that would be otherwise produced during natural interactions. And I remind you that looking at these patterns of neural activity in the somatosensory cortex, and in fact throughout the entire somatosensory neuroaxis, is what we spend most of our time doing in my lab. So the kinds of interfaces we're talking about, again, that's not going to be the focus of my talk either, but with the nerve, there's a bunch of different types of interfaces you can use. So this is the flat electrode array developed at Case. This is the Utah slanted electrode array developed at in Salt Lake City at the University of Utah. This is the time electrode. And so there's different ways to interface with the nerve. What you can do is electrically or pass small electrical currents through these electrodes and produce these very vivid sensations experienced in the hand, as was discussed earlier. With the brain, really, there's only one technology right now that has been approved for human use and has been used to the extent that this kind of work is done, and that is the Utah electrode array. So this is 100 electrodes arrayed over a 4 by 4 millimeter area. So each electrode is about 400 microns away from the other electrodes. And so you can put these electrodes. So another thing I should mention is, as most of you probably know, we have a map of the brain in somatosensory cortex. In fact, we have 4 maps of the brain. One in area 3A, one in area 3B, one in area 1, and one in area 2. And so within these maps of the brain, there are maps of the hand, right, which is right between the representation of the face and representation of the proximal limb. And so if you can put your electrodes there, and we and others have shown that if you electrically stimulate now this part of somatosensory cortex, you evoke sensations that are experienced on the hand, and there are focal sensations. In fact, nearly natural ones. So, and it's been shown, I just want to skip, this is all kind of old news now, but it's been shown that if you introduce somatosensory feedback or tactile feedback through electrical stimulation, in this case of the nerve for a myoelectrically controlled prosthesis, you can vastly improve the dexterity of these limbs. Your ability to do things improves. For example, so this is a movie by my colleague Dustin Tyler at Case Western. None of these things that this subject is doing could be done without these tactile signals. Now, this is a movie out of the University of Pittsburgh. They actually published this recently in Science, showing that so this is now a subject just like Jan, except he not only can control this brain control robotic hand volitionally, but he can also feel through it. So anytime he grasps an object, he actually feels this object through electrical stimulation of his somatosensory cortex. And you can see that. So this is when the prosthesis is endowed with touch, so he can feel the object when he touches it, when he makes contact with it. Whereas in this case, he doesn't. So you just turn off the stimulation. And you can just eyeball these movies and see clearly that he's much better at doing this task when he can feel the objects than when he can't. So this is where we're at right now, I think. The state of the art is, it's been pretty well established in a variety of different contexts for myoelectrically controlled arms for amputees, but brain control arms for tetraplegic subjects, that introducing touch makes you better at using or helps you use the prosthesis. So the next generation of algorithms, though, So the way that touch is, in the vast majority of cases, and I'm going to show you the exceptions in a minute, the way that the touch is encoded is, so you have the output of the sensor on the prosthesis here, right? So this is, so this is sort of a cartoon of what happens when you make contact with an object. The force increases, the output of the sensor increases. You maintain contact with the object, the force stays relatively constant, and then you let go of the object, and the force goes down. And so the way the algorithm works is you basically either modulating the amplitude or the frequency or both of the stimulation to sort of track whatever the output of the sensor is. And that seems like, at first pass, is a reasonable approach. And that's an approach that actually does improve performance. So it's a good first pass. But now if you look at how the brain responds when you grasp an object and let it go, it looks very different. What you find is that at the onset and offset of contact, you have these massive transients where the brain becomes, large swaths of the brain become active. During maintained contact, that activity goes down like tenfold. And then when you let go of the object, again, you have this massive fat phasic transient. And as I'll show you later, that transient actually is inherited from the periphery. So this is throughout the entire somatosensory neuroaxis. You have these neural responses that emphasize these transient events, onset and offset of contact, and very significantly de-emphasize the maintained contact. More generally, so this is just an example of, a kind of a standard example of what happens when you grasp an object, but there's a lot of, in these existing algorithms thus far, there is no consideration of how the neuroaxis actually responds to the stimulation, right? And so the idea of biomimetic sensory algorithms is, let's see how the nervous system encodes this information, and let's, to the extent possible, mimic that. So how, what I'm going to try to do now for the next, however many minutes is kind of give you a sense of how you would go about doing that. So in natural touch, when you're interacting with an object, you have, something like 17,000 nerve fibers that innervate the palmar surface of the hand, including the digits. And a large number of them, thousands of them, are active at any given time during a natural interaction with an object, right? So you have this barrage of thousands of signals that are coming at you all the time. And each of these signals is different from all the other ones. It depends on what kind of nerve fibers it is. There's at least 3 or 4 different types of nerve fibers that innervate the palmar surface of the hand, each of which responds differently to skin deformations. It also depends on where the nerve fiber is, or the receptive field of the nerve fiber is relative to the object, right? So nerve fibers that are at the point of contact are going to respond more strongly than nerve fibers that are away from the point of contact, though they will also respond. So you have this big distributed pattern of activation, and if you wanted to create, restore touch in all its glory, just recreate touch exactly, what you would need to do is, first of all, given a pattern of activation or pattern of contact with an object, know how each of the nerve fibers in the hand would respond to it, and then you would need to be able to stimulate each of these 17,000 nerve fibers to make them do that. Activate each of these fibers precisely and selectively enough to be able to reproduce that. So that's like, there's a scientific challenge of knowing what you want the nerve to do, and there's a technological challenge of making the nerve do that. So, and the scientific challenge, turns out, is solved. So this is the culmination of something like 20 years of work, where we've developed this simulation called TOUCHSIM, which allows us to simulate the response of every single nerve fiber that innervates the palmar surface of the hand with millisecond precision. And this is published, but I'll give you just a quick sense of it. So what it does is first, the user defines what the stimulus is. So it's a spatiotemporal pattern of deformation, or a spatiotemporal stimulus, rather. And then what the model does first is simulate how the skin would respond, because all these mechanoreceptors are embedded in the skin. So first you have to understand how the skin would respond, and then it tiles the skin with all the mechanoreceptors at their known densities, and then simulates, using this relatively simple model, how each of these 17,000 receptors would respond to that stimulus, right? And so the output of this model, so you give it a stimulus, and the output is how all 17,000 nerve fibers would respond to it. And the model can not just precisely reproduce what each, the strength of the response of each afferent. So this is the predicted firing rate versus the measured firing rate to a bunch of different stimuli. So you can see that that's pretty good predictions of the rate. But in fact, it can predict the timing of the responses. So neurons respond through these sort of binary events called action potentials or spikes, and we can predict with millisecond precision when those spikes are going to happen. So basically, we know if you gave me the technology, I could restore the sense of touch. Of course, that technology is nowhere near ready for prime time. This is just to show you I shouldn't say it's not ready for prime time. It's not even in the distant horizon. But this is how, this is just to give you a sense of how the model the model does. If you indent an edge into the skin, it reconstructs how the skin would respond, and then it just reproduces the spiking response of all the neurons. So this has 17,000 units. I mean, there's 17,000 afferents. And of course, we can't stimulate each of these 17,000 afferents individually, as I was saying. But what we can do, what all these technologies that I showed you earlier can do, is stimulate populations of these afferents. And then, how big the population depends on what technology you're using, whether it's extrafascicular or intravascicular. But what we've done, is create simpler models that reconstruct the aggregate activity of populations of nerve fibers. And so, and without going into too much details, what I'll show you is that this model, so what's happening here? The black traces are sort of the ground truth when you have the full model, the ground truth activation of a population of something like 100 nerve fibers, and the red is the reconstructed response of these 100 nerve fibers with a much simpler model that has like 10 parameters. So again, this model allows you to reconstruct, given a pattern of sensor output on your prosthesis, how whatever population of afferents would respond to that time-varying stimulus. So this model is now starting to be deployed out in the field. This is work that was done in Silvestro Mascera's lab, where he found that if you stimulate the nerve with these biomimetic patterns, so patterns that mimic how the nerve responds to stuff, you evoke sensations that are more natural than if you just use the vanilla kind of just tracking pressure, like basically flat frequency trains. This is a pretty subtle effect. But I think what's more compelling, though, is it also confers to the hand greater dexterity. So this is a fragile object transport task, where the subject was either given the standard sensory feedback or this biomimetic sensory feedback. And the subject was able to transport more objects across this barrier without breaking them with the biomimetic than with the standard feedback. So this shows the data. I'm running out of time, so I'm going to fly through this. Now, Greg Clark's group at the University of Utah implemented this model, was able to reproduce Silvestro's task, but also did a compliance discrimination task, where subjects were to discriminate 3 levels of compliance. And what he found is that the subjects were much better when the sensory feedback they got from the hand was biomimetic than when it was standard. So this not only allows, it's more naturalistic maybe a little bit, it confers greater dexterity and conveys more information about the object. So this is what the data are. So I have two more slides. The first thing is, I told you already earlier that the aggregate activity in the cortex, in the brain, really follows the aggregate activity in the nerve, right? If you look at the single cell level, there's huge differences. But if you look at the aggregate level, they're very similar. And so the nice thing about that from a prosthetic standpoint is that you can use these algorithms that are developed for the nerve in the brain, right? And that's just starting to happen. I'll show you one little data point that, fresh off the press or whatever, hot off the press of, so this is my colleagues at Pitt again, who had the subject, Nathan, that I talked to you about earlier, discriminate or judge, rather, the naturalness of fixed trains. So now this is trains of stimulation developed to somatosensory cortex or biomimetic trains, so trains that that Chris, a student, developed based or derived from our model of TOUCHSIM. And you can see that on an overwhelming majority of cases, the subject preferred or thought that the biomimetic stimulation was more natural than the fixed stimulation. Of course, the really important test will be to see whether it confers greater dexterity to the bionic hand, and that is soon to come. I just want to give a shout out to all my many collaborators, and I'll point out that Max is one of my more recent additions to this list. And unfortunately, we published a very cool paper recently that I couldn't really squeeze into this talk, but I'm happy to talk about it if you ask me about it. And this is my lab and my funding sources, and thank you for your attention.
So we have one question for you. What are the limitations of peripheral nerve stimulation for sensory recreation, and what type of things are hard to simulate?
Right. So I think the limitations, the sky's the limit, and the engineers just need to get better at their jobs. It was kind of one of the themes. I'm just kidding, but not really. I think one of the major limitations right now, as anyone who's worked with peripheral nerve stimulation will tell you, is that you're just kind of blasting currents in the nerve, and they're just willy-nilly activating a population of afferents, right? And during natural touch, these afferents are never co-activated together because they have different response properties, right? So, for instance, one afferent when you press into the hand will go bzzz, and then another afferent will go bzzz, bzzz, and only respond to the transients. But when you're electrically stimulating the nerve, they're all responding, they're together, which is one of the reasons why you have these really paresthetic sensations. So that's, I think, one of the urgent challenges, is to be able to do more selective stimulation.
Great. Thank you. Thank you, Dr. Bensmaia.